Okay, thank you very much. What I'm going to try to do in these lectures is to go through uh, two different aspects of statistical mechanics that I think that to distinguish them is interesting for people who do systems like granular matter or activated matter. So when we talk about statistical mechanics, what do we think of? So here I have a citation of Boltzmann. You always have to quote Boltzmann. The molecules are likewise just so many individuals having the most varied states of motion, and it is only because the number of them that have on average a particular state of motion is constant that the properties of the gas remain unchanged. Blah blah, and this is of course just concentration of random variables, and of course for us is completely natural. It's amazing. He takes 3 paragraphs just by repeating on and on the same thing. For us, this is, of course, completely straightforward. This is what we are told at the beginning of a StatMech course, the fact that you don't want to know the details of every molecule, what they do, and then a statistical approach has to be used, and so on. So this is the aspects of, let's say, macroscopicity. The fact that we are doing a macroscopic description, of course, this is also what hydrodynamics does. And here, from here, we have a certain number of notions that will be important. The notion of something that is extensive, like energy, and doesn't fluctuate. Fluctuating versus non-fluctuating quantities. You know that if you ask what is the speed of molecule number 27, this is a fluctuating quantity. But if you ask in a little macroscopic box what is the distribution of total energy, this is a good thermodynamic question to ask. Then you have notions of symmetry breaking, like in a ferromagnet, and phase transitions. You have, in more developed levels, topological considerations. For example, if you're studying defects, you have these things in activated matter. And is still even more developed or scaling notions, and so on. So all this comes from deciding to do a macroscopic approach and deciding to consider quantities that describe large ensembles of individuals and looking at the right quantities. Now, there is a completely, and usually not very much distinguished, a completely different line of arguments that have to do with the notion of equilibrium. Now, equilibrium, as we shall see, and I will insist, and this will be the topic of 1.5 at least lessons, is a property, could be of your system, but at the very least could be of the thermal bath you use. And what I will try to convince you is that equilibrium is a symmetry, a very particular symmetry that in fact is a time reversal symmetry. You will see that this is not as mysterious as it sounds. And it's a symmetry that your bath has, and maybe your system, if you give it enough time, it will inherit. As you see, it's important to realize that this has, in principle, nothing to do with these other kind of considerations. So what do we get from equilibrium? Well, we get a number of things, the typical things we study in the StatMech courses. One thing we get is what Meran did just now. Forget about dynamics if you want for one-time quantities. So for one-time quantities, you can forget time just by using, for example, the Gibbs measure or microcanonical measure. And this is only, and I will try to hammer this a lot, this is only thanks to equilibrium. Nothing, so equilibrium is, as I said, a time reversal symmetry, and only by virtue of the existence of this time reversal symmetry, you are allowed to calculate things without actually doing dynamics. And of course, you get first and second principles, which are the subjects of thermodynamics. You get a series of impossibilities. You learn that you cannot do a perpetual motion machine. You learn, so you have impossibilities. And also you have the fact that you can, which is quite admirable, that if I have a thermometer, I can plug it in a system in equilibrium in different places, even if the system is not necessarily homogeneous, and it will measure the same temperature. And furthermore, any thermometer will measure the same temperature. This is a form of transitivity of measures, which I will talk quite a lot about. And this is something that only thanks to equilibrium we have. So my plan is, in these 3 lectures, is to first of all convince you that equilibrium is indeed a symmetry, a time reversal symmetry. Second, sorry. What happens when we don't have that symmetry? What do we lose? And the last thing I would like to do is one model out of equilibrium, but macroscopic, to measure, to solve it exactly. Why do I do that? What is the idea? The idea is that I would like to decouple these 2 concepts the best I can. So first of all, I will try to insist a lot of what are the incredible miracles that equilibrium gives us. Then the fact that as soon as you put 1 foot out of equilibrium by doing anything to the system, you lose them all. And basically, you can fairly say that you have very little that you know how to do to replace these principles. But that has nothing to do with the fact that still a macroscopic description gives you something. What it doesn't give you is a measure that you can calculate without dealing with dynamics. So when you're out of equilibrium, even if you're macroscopic, you have to solve the full dynamics. It doesn't give you something like the second principle, and it doesn't give you transitivity of measures, so you cannot define state variables just by sticking your thermometer in different parts of your system and getting the same result. You don't have that. Yeah, and you don't have inequalities in such a nice form as you have in equilibrium. So as people who are mostly interested in systems that do not have equilibrium, you will see that you lose a bunch of things. A lot of the literature of activated matter is dedicated to unlearning this, but still applying, using the macroscopic and statistical description. Okay, so and then if I'm lucky, today or if not tomorrow, this is for Olivier, just to convince him. Imagine you have water and you have a trap, a fish trap, and you have a fish inside which has fallen into the trap. So, question, how can you free it without touching it? Just by application of the principles of statistical, out of equilibrium statistical mechanics. And the question is, the answer is very simple. Of course, it had the possibility of entering. So, just by a simple application of the laws of statistical mechanics, or let's say by a simple understanding of what equilibrium and non-equilibrium mean, you can just by some simple manipulation free the fish. Okay, so and this is an experiment that should be done, I think. It's not a hard experiment to do, as you will see. Okay. Okay, so let us start. So now I'm going to so today's lesson is going to deal with equilibrium, and you will see how we get the restrictions. So what I'm going to do is going to outline rather than do a very traditional classical calculation that I think it's first attributed, I think, but to Zwanzig. And I am following the lectures of Letizia Cugliandolo here in Les Houches, but you're going to find the better if you Google this, you're going to find the latest version, which probably is Google that and you will get the version of last year. So I'm following basically this, which is a very compact presentation. So what we're going to do is the following. We want to understand how a heat bath works, and we want to understand how an equilibrium heat bath works. So the strategy is the following. You have a system whose variables are P and X. Momentum has a potential V of X, an energy and we want to construct a heat bath. So what would a heat bath be? Well, anything that I can guarantee is in equilibrium. But that's not good enough. I want something that I can solve explicitly for the bath, not for my system. So the clever thing to do is to consider a set of harmonic oscillators, many of them. So so you have many harmonic oscillators with their own masses, which for the moment I'm not telling you what they are. I have, this is the Hamiltonian of the system, and now I want to couple them. So the way to couple them is linear. So to make it easy, it's not necessarily so, but CA are constants. So it's a linear coupling. And because I have this linear coupling, and these are harmonic oscillators that I will kick out of, I will integrate away, I will just integrate over those, I need to add a counter term that will cut off this extra energy that I'm paying. So I have the bath, I have the system, and I have a connection, and some energy is lost in that connection. But we would like to analyze this system separately. So it is necessary, and you will see it, how this comes in the calculation. You need a counter term, so that what happens is that the Hamiltonian of the bath plus so, oh, sorry. So you see the counter term I added is it's a square of the last term. You will see that this is just to guarantee that the measure that I get is e to the minus beta times p squared over 2 plus 2m plus v, and nothing else if I eliminate all the oscillator variables. That's the only thing. But this is a minor technical point. You will see that it's a natural thing to do in the calculation. That's not the hard part of this calculation. Yeah. Why, sorry? The coupling, you could choose whatever you like, but we want to make it as easy as possible for the bath variables, which we want to get rid of. So I could have put anything that contains x and q, but I keep it linear in q. Actually, I could have put x squared here, and it would be perfectly okay. I could have put q cubed also, but if I did that, then I will not be able to explicitly eliminate the bath. So this is not important. Anything should do. If things depended too much on that, it would be worrying. Okay. So now the strategy is the following. We write all the equations of motion, both for the bath and for the system. They are coupled because they are coupled. The systems are coupled. And the equations of motion for the oscillator, if you do not consider, if you take x and p of the system as simply not known, you can see that the equations, we will see that the equations for the oscillators are linear, so we can solve them. We can plug that into the solution for the system's equation, and we will be able to obtain an equation for the system in contact with the bath, but the bath is gone, and that equation for the system will end us by giving us how does a system behave in contact with the bath, of which you have completely eliminated the variables. Okay, so this is more an outline than a calculation, but you can check. None of the steps is hard. Okay, so none of the steps is very hard. First, the equation for P. Let's make it simple. This is just, I have differentiated the total Hamiltonian with respect to the, and now the equations of the bath variables. So you see that this set of equations, they talk to one another because X, which is the system, belongs to the system. Yes? Here? Uh, no, because I didn't put the system yet. That it is made precisely the counter term, we added it so that this is a perfect square. And you will see that that's, but then the, I think I get it right. Oh, sorry. No, no, no. There's an X, yes. So at any rate, here there is an X for sure. No, sorry. Here, no? I'm not missing. Yes, sorry. Sorry. But still, the point remains, it has to be a perfect square. But yes, you're perfectly right. Okay, so these two equations talk to one another, and it's important because it means that not only the oscillators, that is to say the bath, is bothering a little bit, perturbing my system, but also my system is doing something to the bath. And this effect of talking in both directions is very important, and we'll come back in several occasions. So now, this equation I can solve considering x of t without explicitating x of t. And I'm going to first write the result and then we will discuss it. So when you solve it completely, what you get is an equation for x. So you get this equation for x where you will see that this and this term are related to the things that we're missing here. I think that there's an x. Yeah, sorry. I missed an x in about two. Okay, so if you solve these equations for q, you will get this equation, but with gamma this is a place where the counter term turns out to be useful. So yes, you're right, there was an x here. So gamma and psi up to this time, they are only definitions that I wrote for short, but the only thing I did is solve for the QAs using this equation, plug it in here, and it gives me these two terms. The first term comes from the initial condition. These are the initial conditions for the bath. These are the initial conditions for the bath. And then they evolve because they are oscillators through sine and cosine. But notice that x is playing a role for the here it's an x. Here notice that it's playing a role for the whole evolution of the things. So now let us pause for 2 seconds and see what we have done. We had oscillators that just went away, and because I solved them away, plugged them into the equation, and then I discovered that I can write this equation as a usual Hamilton's equation with a time-dependent noise that depends on how the oscillators or what they are doing, and through this memory term, also you can call it a friction term because notice that it is integrated times a velocity. It depends on the velocity, and these two terms come from the bath which we have solved away. Okay? Now, what would you have to say? Up to now, we haven't said anything other than the fact that the bath is in equilibrium. The fact that the bath is there. Now, we want to say that the bath was in equilibrium at the initial time. Yes? Yes, but in a way that it's a perfect, that you will see that it is, in this bracket, you will see that x will go away. No, but you will see that it's this factor. So in the Gibbs measure, this factor you can rename the variable. That's the reason why we added. This is a quantity that yes, it's x of 0. Yes, you integrated it. Yes, sorry. Yes, so that's you integrate it away and it goes away. So what do we have to say to be able to say that this is an equation that has an equilibrium bath? Well, simply start with our oscillators in equilibrium. And then we will have to make some choice of the omegas, of which I had said nothing. I didn't tell you even how many oscillators I have. I said many, but many could be different things. I didn't say anything about the masses. But the main point is that we want to say that they are in equilibrium. Okay, and then only later we will decide something about the omegas of the oscillators we have chosen. So if they are in equilibrium, what this means is that this entire problem with these two things and this term have to be in equilibrium at time 0. So at time 0, you want to say that the probability is proportional to e to the minus beta. This is the first time a temperature enters your problem. You want to say that. And now we see that this integral can be done. Sorry, I said proportional. You should divide by, of course, the normalization constant. So you see that for the pi's, it's a Gaussian because this thing is a quadratic. Sorry, did I didn't. I should have added the momentum. So for the bath, it is a Gaussian. For the thanks to the fact that I added this counter term, this term is only a translation. I can just shift the variables here, and it will be a Gaussian too. And what are these two variables when I look at them? Sorry, here. I forgot to write. So these two variables are two Gaussians because the only place where randomness enters, where the distribution enters, is through what this is and what this is. And now, this is a step I am not doing, but if you average these things, now this and this variables, this and this become random, and what we find, or this variable becomes random, and what you find is the result we were looking for. because the pi's and the q's have zero average, psi inherits a zero average. And this one is a bit longer to do. When I say average, I say average over the initial distribution of the oscillators. Not necessary. For the moment I didn't, because in the fact that I completed the square here, x is not used for that variable. You don't need to assume it is in equilibrium, fortunately, because it's going to be useful, this equation, for things that do not start for the system in equilibrium. So averaging over this up, which I will also say it's the average over the bath or of the noise realization. It's a longish calculation, but you have to simply multiply the sines and the cosines at 2 times, and then average over the initial distribution, and you get Is it P O Q that is proportional? Sorry. Isn't it a big enough P? Sorry. Okay. Yeah. Now I'm okay. Okay. So what we did up to now, let me recap. We had oscillators that were coupled to my system. Next, I didn't specify what they were, but I next said that they started their lives in equilibrium. Then I solved for them without any assumption. X played a role as a kind of external field as seen by the oscillators. Then we could eliminate them, and this led to this equation, but the equilibrium condition added to this equation the condition, which I'm going to copy down here too, that the variance of this variable, the correlation, sorry, of this variable is the temperature times this very same factor that appears here. This is a Gaussian thing, but I didn't say what is gamma. No, the only thing that is Gibbsian is the harmonic oscillators themselves. Because the counter term is there. But it's in the counter term, I think. In any case, okay, it is here, and when you assume that the measure, sorry, it's Gaussian with respect to the bath. You're not assuming that it's with respect to x. That's for certain. Then this term drops off completely. Sorry about the counter term, but maybe a clarification will help. If I have this, and then I have one oscillator that is acting as a bath, so Q times X plus, well, I don't know, Q squared. And I put a beta here. So imagine I integrate this bath away. I get this, but then I integrate this, and this gives me beta x squared. But this is an undesired term, which came from this interaction. It's like the link has captured some energy. So in order that this doesn't bother me, I need to add a pure term like this, which wasn't in V, but is there to subtract the energy of the link, let's say. This is a famous counter term, and there's plenty of speech about this in articles, for a reason that I will say in a minute. So, okay, I'm sorry for all my typos, but so what we get at the end of the day is this equation. We get an equation where our system, which I assume has 1 degree of freedom and nothing else, has a noise that it feels, for which I have an expression, and has a memory kernel, and the bath is here and here. This, as it is now, is what is called the generalized Langevin equation. For some gamma and some psi, of which I didn't say anything, except that they have to be related like this. The information that the bath was in equilibrium to start with is here, and nowhere else. So what can I do about this? Well, actually, you can do many things, and the literature is full. Gamma is a symmetric function. It could be something like this. We will say that because this is the autocorrelation, this is colored noise in general. Of course, this is generated by the omega. So when you choose the omegas, you are choosing the form of the gamma. But because this is a sum of signs, you can generate pretty much anything. So in general, you don't have to assume anything special. Gamma could look like this. And that's all. You can even, if you take many or sufficiently many signs, many oscillators, you can generate a gamma you want. And that's as general as it comes. And we are always in contact with a bath. Now, for simplicity, in general, very, very often, we don't work with a bath that has colored noise. Yeah? Yeah? Well, no. Wait, no. Sorry, because you're right, the Q wasn't there. Sorry. Sorry by these mistakes. In any case, this is the generalized Langevin equation, and you can use it, and sometimes you are forced to consider a noise that is non-local, that is like this, colored noise, because your physical problem, your true oscillators of your physical problem are like that. But if you only want matters of principle, you can go to a limit where gamma is a delta function. And this is called the Markovian limit. It's simply one kind of bath, but it's a bath that is much more pleasant to do actual calculations. And then if you go to that limit, what you get is this equation. So I'm putting here a delta, and well, x. And now you're forced now to say so the logic now is that I got this equation just by considering a lot of oscillators. Now I chose specifically the distribution of oscillators with the frequencies so that the noise is now a delta, and the memory kernel are local in time. This is a Markovian limit. And this is what is called Langevin equation. This is what Mr. Langevin Probably he didn't go through this calculation, he just dreamt it. But for a molecule in water, he just considered, of course, a molecule in water is not in interaction with oscillators. So, and there's very little you can actually prove there. Actually, if you want to be more serious, you would say that it's not even literally true that it satisfies this equation. With oscillators, you can play this game and do it completely. Yes. 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 Yeah. Okay. Yeah. So you see, what translating what Julian says, imagine that I had one oscillator. Even if it was random, its amplitude was random, it's only going to be an oscillation. So clearly, that's not going to give me a noise. To get a white noise, I need many, many, many. If the number of oscillator is finite, I am summing oscillating things. When you sum oscillating things, what happens is that for some time the correlation goes down, but then there are resurrections and all sorts of things. Turns out, but this is a whole theory of mathematics, in the limit where you add many, many, many oscillating things, the resurrections of the correlations go to infinity. Why? Because three oscillators start in some phase, and after a long time, if they are incommensurate, the frequencies, they will align for a moment and come back to their original situation. In order that you can really think of this as a random noise, you need many oscillators. Random it is, because the phase and the amplitude are random. But if you want really to consider in time that the thing really is a random noise, then you need many, many oscillators. Most mathematicians would not accept this as a proof, so there are proofs where you actually have to study how does a sum of oscillating things with random phases, how does it really work and dephase and then go to zero and so on. For us, it's okay, but it's a bit illegitimate in the sense that, as Julien says, the bath itself has been equilibrated because I declared it in equilibrium, but it being an ensemble of oscillators, really it's not chaotic at all. But that is a step that we will sort of forget for a moment and take this derivation as for many oscillators and then accept that in this way I can generate a true bona fide noise. Yes, and this is the entire subject of quasi-periodic functions. It's a question of when I add sines and cosines, these resurrections, when do they happen? It's an entire subject in mathematical literature. You are advised not to enter that region. Yeah. Yes. You're going to get a better, a more general version in a little while, tomorrow, where I am going to show you that just as your oscillators had some condition and that this will have an effect on your system, and the condition is this one, the system itself, if it manages to equilibrate, whatever the system is, can serve as a bath for another system again. So this is a property that can be inherited. So it is an answer to you because it means that my system, whatever it is, if it is equilibrate, it can be used as a bath. And it doesn't need to be oscillators anymore. This we're going to do tomorrow. Yeah. Maybe, maybe, and it's an interesting thing to explore. Uh, I need to be able to integrate away everything, so I need to have Gaussians, which is the only integral I know how to do. And yeah. Now, you say, couldn't I? Well, this problem arises because sometimes you want a bath of spins, and then you need to think a lot. You can do it, but you need to think a lot. But it can be done. The logic is always the same. You have a system of many, many actors that are trivial, but can be so that they can be wiped away, and then the memory they leave on your system is a noise and friction that have to be related in through this. Yes. Whenever you get rid of a variable in a system, you get non-locality. That's a rule, a fact of life. In this case, it's a non-locality which you can treat completely because they are oscillators. One lovely thing of this problem is that you can see that you could play this game in quantum mechanics because linear oscillators can be solvable also in quantum mechanics. And this tells you how to make a quantum bath. And it's not terribly harder than this exercise. But when you do it quantum, you discover one nasty fact is that you can never make a Markovian limit, but that's another story. But it's nice because it's a way to think of these problems that I find very efficient, and it's a pity that it's not taught in general in the courses. So let me say this, that I could also do it with many variables, each one of them with its own private bath, okay, which you integrate away separately. But the logic is identical. Yes? Yeah. There's a bit of literature on that. The literature on all these subjects is infinite, as you can imagine. It's a mess. First of all, there is the technical mess, and then there are cases where it's amazingly difficult to show things, and this is unfortunate. Of course, if you have many things, each one coupled very weakly, then you can use things, and you will see an example when I'll do it tomorrow. What I will show you tomorrow is that any system, once it has equilibrated, it's a good bath for another system. And this is crucial because it says that equilibrium is a property that you inherit, that is transitive. Okay, so this is the Langevin equation as we usually find it in books. And now there is an additional simplification that is optional, which is to consider that this term is absent. This is the overdamped Langevin equation, which then only contains this, and it has a 0 here. That is perhaps even more common. Okay, so now I want to say a few things about this limit, a few technical things that you will come across very often, and probably if you did, even in active matter, you would have come across very often. So imagine now I have the overdamped equation, so it's something like this. Oh. So this says that the velocity is equal to something plus a white noise. Now, this already means that the velocity is not a very nice quantity in the overdamped case, because a white noise is the ugliest possible function you can imagine. It's something that is decorrelated at any two subsequent times. So you get a lot of problems. For example, if you want to calculate work, which is force times velocity, and integrate, how do you do force times something that is so ill-defined? Just already you can see this from here. So this, how would I do in the most naive possible way? Well, I can go back, reinstore a little bit of um, of inertia. If I have inertia, now you see what is not well defined is the acceleration, but the velocity is smooth because this term has white noise, but this term is the time integral of the acceleration, so it's going to be much smoother. So the not smoothness, you see why? Because if I have an acceleration which is a white noise, the velocity is the integral of this over time, so it's smoother. And if even that wouldn't be enough, well, then I can go back to this equation, put here a kernel that is, to my taste, sharp enough, and then everything is perfectly okay. No, there's nothing that is wrong here, nothing that is ill-defined. But many times you still want to calculate things with the local equations, the Markovian ones, because they are easier in so many senses, which you will see now how many things you can do much more easily. Now, you could do something a bit different. You could try to give these things a real mathematical sense. And this is what is called itocalculus. You will find it a lot in literature. It is telling you how you have to understand and how you have to compute stuff with quantities that are as nastily defined as these ones. So a word of physical common sense. It depends. If you want to know how to, itocalculus, once you know it, it's very powerful, they tell me. And you can do calculations in an efficient way. On the other hand, if you have conceptual trouble, it's safer not to get into things of calculus and going back, at least temporarily, to a non-local equation. Think of the things in the way they are when they're well defined, and then try to think how the limit is recovered. Okay, so this is very, very closely analogous to when you want something to be very sharp. Of course, you idealize this with a delta function, and when you want something that falls like this, you idealize this with a Heaviside function. These things were invented, I think, by Heaviside, and Dirac obviously worked on this, but without any special mathematical construction, just saying, okay, I'm considering a Gaussian that becomes narrower and narrower. Of course, then Laurent Schwartz made a real mathematical theory of distributions, and of course you're free to learn it, and it has its powers. But if you want to be simple-minded at the level of physics, you usually don't care so much about the theory of distributions. You use them. I mean, nobody, as far as I know, studies distributions when they study the physics course. So the same is true about itocalculus. It is powerful. It can be used. It tells you how to treat these variables without going back to the regularization, but you can always, if you want to make physical sense, go back to the regularization. Okay. Okay, so now we have these stochastic equations. In fact, we have two of them, the overdamped and the one that is not. And so let me write them again. And no, I won't write them again, but I will add the possibility. I could have done this at the very beginning. Sometimes I'm going to add, and this might be interesting in the present context. Here is the force the variable on your system is feeling. You could add to it and I will sometimes do this, a force here. The only reason why I distinguish this force is that I'm going to say that this force does not derive from a potential. I have the freedom in this equation to consider that my system has forces that don't derive from a potential. Forces that don't derive from a potential, you already realize they will ruin your equilibrium because they will make currents in your system. This is one of the ways of ruining equilibrium, subjecting your system to forces that don't derive from a potential. So I will always allow for this possibility. Of course, it will be more in preparation for what comes later, which is precisely what happens when you lose equilibrium. So consider this as an optional. So this one is called in the literature the Fokker-Planck equation. Sorry, not the Fokker-Planck. This is just Langevin overdamped. Okay, so now these equations you can treat them in, these are equations for trajectories that depend on a noise. And you have an ensemble of trajectories. If I do the same experience with different realizations of noise, I will get different trajectories. There is another description, which is I could study what is the probability distribution at each time and write an equation for this. So imagine you have a computer, you generate a trajectory with this one, then you generate another one, then you generate another one, and at the same time you look at what is the distribution of x you make a histogram of x at time t, and you get this probability distribution. Instead of doing this, you could write an equation directly for the probability distribution. It's equivalent, and it's another way to treat the same problem. Is it okay? So the equations you can prove, I'm not going to do it. You can follow an easy derivation in this. Now it's my Les Wouche lectures of some years ago, which is called it's in ConMat. You will find it in many books, but there you will find a simple-minded derivation. And so it turns out that for this system, so I put this operator here, and this gives me the evolution of the variable p. And this one is called, I think unfairly, the Fokker-Planck equation, usually. I believe that it should be called Smoluchowski equation, but I think nobody does. Okay? The forces, I added a minus signs for matters of taste, but so it becomes a plus here. The force will ruin the equilibration, but you can still put it there. And you can also, of course, treat this in as many dimensions as you want. Okay? If instead you want to treat, you don't want to throw away the inertial term, then you get a nastier equation where both P and Q will appear, and you get Now it becomes this one is called the Kramer's equation, and the evolution is ruled by sorry, where are we? Okay, so several things to note. I sometimes don't, I sometimes omit the sums, but of course you can. So several things to note. It was easy for me to throw away the inertial term. For example, I would say if the mass is very large, then I throw it away. But here, throwing away p's is by no means easy. You have an equation that lives in a space that contains all the x's and all the p's, so it lives in phase space, and describes the evolution of a probability in phase space. Here it describes the evolution of probability in configuration space. You've lost all information for the velocities. And as I told you, the velocities themselves are very ill-defined in the overdamped equation. So going from here to here is a hard exercise when it can be done. And this you can find, if you really want to see it, in the book of Risken. In fact, everything can be found, everything related to this subject can be, or a lot of things can be found in this book, which I recommend. And of course, this book, as well as all the references for this part, you will find here. Okay, so now we have gone a long way from the original problem of a system coupled to many oscillators. We got rid of the oscillators. This gave us some extra terms that represent the bath. And then in the Markovian limit, we manage rather easily, we didn't do it here, but it's not terrible. We managed to obtain equations that describe how the probability over many realizations would evolve in phase space or in configuration space. And now comes the part that I advertised at the beginning. So these equations you can solve, and we'll tell you to what the distribution tends. So this is a Markovian limit. I will erase this. We will not discuss again. Oh, we will, and I think for Ludovic Berthier's talks is going to be important, the non-local Langevin equation, and you will see why. But technically, we are not going to discuss much. But from any one of these equations, just like when you study Schrödinger equation, you can formally solve it. Of course, this is not helping you a lot, but this is an operator. And you can explicitly write what your distribution is going to be at each time. Notice that this is exactly the same thing you did when you studied Schrödinger equation. The only difference is that there is no I here. Also, this operator resembles a lot, the one I erased, resembles a lot Schrödinger's equation. And the same is true here. With a Kramer's operator, and then you start from here. So you can also write this in this way. The probability of starting in x0 in any number of and the same is true here. So already this gives you what is the probability of transition from any point to any other point. Very well. So now, one last technical thing for today, and we are done technically for today, is the following. I will do this only for Fokker-Planck, only for the overdamped case, but you can do very similarly, and I will tell you how to Kramer's. But is it okay? So remember that the Kramer's operator, the Fokker-Planck operator, is maybe with a minus sign. So first thing is to prove this. So if you multiply this way, you get this symmetry. Let me show you how you prove this. This is a hint, the only thing you need to know is that what is this? This can act on this one or act on whatever you have on the right. So if it acts on this one, you're going to have a minus beta v, sorry, minus dv dx. And then this will pass here and will cancel. Otherwise, it will act there and it will cancel directly. You agree with me? So this derivative either acts here or it acts on whatever it has on the right. If it acts on this one, it takes down a derivative, and then this exponential will cancel with that one. If it simply acts on whatever is on the right, it acts on whatever, and the exponentials cancel. Now, when you have a thing like this, it's a change of basis of a matrix, you can do it operator by operator, because you can insert all the e to the minus betas you want. You can insert it here, e to the minus, e to the plus, e to the minus, e to the plus in every operator. And just by using this every time you need it, you immediately get that this one is equal to this one. And you realize that this one is h dagger because this is just integration by parts. Okay. So, what is the interest of this? And this is the formula that I wanted to, perhaps the most important thing today. This is just by definition. When you turn round, you get the dagger. And now I use this property, and so I have to apply it to the dagger. So this is sorry. Okay, so, and you can do exactly the same thing for Kramer's with inertia. The only thing is that you have to reverse the velocities. I'm not going to do it, but you have a symmetry that is very similar. But for this one, I used explicitly, in order to say this, I had to use, if I am in many dimensions, this is also true. In one dimension, it is always true. In many dimensions, it is also true. But this kind of symmetry is only valid if Fi is 0. In other words, if all the forces derive from a potential. If not, there is no such symmetry. Yeah. Yes, not a path. Perhaps you would like an intermediate step, which I will do it. So as an intermediate step, I could have done this. As an operator. So you see that this is evaluated in x1 and this is evaluated in x0. Yes? This is why you want a bath. Yes, but yes, sure. But yes, but you know that whenever you have t a t minus 1 equals b, let's say, it is also true that t of f of a, t minus 1, well, for example, it is true that t of a squared, t minus 1 is t a t minus 1 times t a t minus 1, which is b squared, and it's true for any function. So every time that you transform something, you can plug it into whatever you have. This is what I did with exponential. There is this extra step, if you prefer, that allowed me to take these things away. Okay, so what we discover now, after much suffering, is this symmetry property, which I'm going to rewrite here in a way that is going to be more familiar to you. Which is the following. Probability of going from x0 at time t0 to x1 at time t1 times e to the minus v of x0 is beta, excuse me, is equal to probability of going from x1 at time t1 to x0 at time t0 to x0 at time t1, so the reverse thing, times, this is what we proved. This is for Fokker-Planck, and for Kramer's you can prove basically the same thing, but with a small variant. There is this sign that is important that you have to reverse. And you know this property from this one? This is what is called detail balance. Okay? But for us, it's going to be... Sorry? Yes, absolutely. So here it is 0, here is 0, here it is 1, and here it is 1. Yes, sorry. So for us, it's detail balance, this one. This one wouldn't count in ordinary life as a detail balance. In a computer program, you wouldn't call this detail balance because it contains a change of sign of some variables, the p's. But they are both time reversal. Is it okay? The point you have to retain of this is that after so much suffering, we discovered that this dynamics in contact with a heat bath has a symmetry when these are true, when the forces that don't derive from a potential are 0. Or in other words, when all the forces derive from a potential. If you add a force that doesn't derive from a potential, you will see that these terms this picks up extra terms. So these symmetries, and this will happen always when you are in contact with a thermal bath, you will always get a thing that tells you a relation between going from here to here and going backwards, with the additional element that if there is a p, the going backwards implies a reversal of the sign of the p's. It's not truly going back, it's going from the point x0, p0 to x1, p1, or going from x1 minus p1 to x0 minus p0. Okay. It's nasty. I, 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 I tried to do it in an easy way that wouldn't use path integrals for this course. And I decided that there was no easy way I could find. Uh, and I haven't seen it in the literature either. But it has to happen. This does not depend on you being Markovian. The symmetry here is capturing, it's telling you my bath is in equilibrium at temperature T. And remember that temperature appeared because of this was the temperature at which our original oscillators, now gone, were in their equilibrium. Okay? Fi is a notation which is abusive, which says this is a force that doesn't derive globally from a potential. It acts on the system. Yeah. It wouldn't have done anything. Oh, no problem. No. Yes. Yes. There was, yes, because as a, you can, because you have, yeah, you have something like this. When you transform a term like this one picks up a minus beta ddv. If there is an fi, this will not happen. The bath, exactly. It does not matter for the derivation of the equations. It doesn't matter for Fokker-Planck. It does matter for Fokker-Planck or Kramer's having this symmetry. Having this symmetry, yes. This matters. There is a much nicer way to write, for example, this one due to Kolmogorov that I find incredibly simple and elegant, is that you can apply this twice and convince yourself that this and this are the same. Why? Because you apply this 3 times, and what happens is that you get e to the minus b1, and then you get plus e to the and then minus, and all the exponentials cancel, and so you conclude that p of going to from x0 to x1 times p of going at given times to x2, p of going to x2 to x1 0 again is the same as p of going to x from x1 to x1. Sorry. What am I missing? This is x1, x2, this is x here. No. Yeah, yes. Yeah. Yeah. Okay. So, this already tells you something nice. It tells you that the system, and this is still when you have these thermal baths will not make you go round things. For x. This is for this one. To write something similar for this one is a little bit more involved because you have to take into account the signs of the p's, and it's a bit more nasty. But for this one, you can see very easily that it is the same thing. And you can see that both formulations are equivalent, in fact. Yeah. Okay. No, you want to me to justify the counter term, no? Yeah. No. Ah. No. You can do it with F. There's no problem. But it doesn't. You're full of. Let's say. In fact, if you have an F, then you don't have equilibrium at all. So you have to be careful. You have to write the equation of motions for the oscillator and then say that those oscillators have a given distribution. But you cannot write a big Hamiltonian that also contains, when you have, when you have forces like this, for example, you cannot write this as a Hamiltonian equation that derives from a Hamiltonian. So you shouldn't try to write this for the initial configuration, or even, so the only thing you can do is talk about the distribution of the axis. In any case, it can be done. It's not. Yes. Where memory is important? Yes, the most famous one is, it's quantum though, but that doesn't change much. When you have an electron that lives in a crystal, the thermal oscillators are real oscillators. They are the Fourier modes of your sound, the phonons. And the phonons have their own spectrum. You cannot choose it in 3 dimensions. You have all the boundary conditions of your phonons that give you a spectrum of phonons, which you know. And this, you're not free to choose. It doesn't give you a Markovian thing, and it is very, very important for the physics of an electron that lives taking as its own bath the phonons of its own crystal. And there they play a very important role. This is called the Ohmian, for Ohm's law, no? The Ohmian. And you will find this in quantum mechanics. It happens very often. So yes, it is important. Unfortunately, many of these things get very nasty when you try to do them non-locally. And furthermore, the literature is very, it's at the same time excessive and incomplete on this subject. So it's very messy to find your way. But conceptually, the Markovianness is not so important. It shouldn't really change so much things. So just for the last 5 minutes. So we discovered a law that tells you something about time reversal. And this time reversal symmetry, we discovered, is broken by forces that don't derive from a potential. It will also be destroyed if the potential depends on time. This will also destroy this symmetry. And it's going to be, these two things are going to be 2 of our favorite methods to kick a system out of equilibrium. Of course, active matter has all of this, so we can have all of this. So active matter will not have this time reversal symmetry. What we will do is explore the consequences of this and try to put this as a contrast for how these things break down when you're really working for systems that don't have that. Let me give you a very, very simple example. Let's start with a fish. So you have your fish. This, I don't know, in English it's simply, I think, a fish trap. In French it's called a nasse, I think. And I learned, thanks to this, that it's also the same word in Spanish and Italian, but I didn't know this. So, okay, so your fish entered there. But now you have the x's that are here inside and the x's that are outside. And the potential other than the wall is 0. So if the fish would be Brownian, the probability of an x inside, one particular x inside to one particular x outside, is of course the same, because there's no potential, as the probability of x outside to that x inside. But of course, I have to integrate for all the x's that are inside and all the x's that are outside. The morals of this is that the probability of out is the volume of out divided by the volume of in, which is the same as saying that in equilibrium I am equiprobably, if I am swimming randomly in contact with a thermal bath, so the fish is so small that it suffers Brownian motion, then its probability of being inside, detail balance tells me, to the extent that of course it is following a Langevin equation, it tells me that the fish will naturally, if the volume outside is much larger, will drift away. Now the fish is not Brownian, it has its own rules of motion, which it thinks or it's genetically prepared to swim in that way. So how do you get rid of that? For the fish, this is catastrophic because the ways in which he swims doesn't allow it to go out, it seems. So the way to free the fish is to put some drug in the water that will make it so mad that it will not apply any of its strategies and just swim randomly, and this will guarantee that the fish will get out. And I'm trying to convince Olivier that we do the experiment. I'm saying, because I think it would make an irreproducible result, probably. But you see the point. Let me give you another example. A ratchet. A ratchet is a potential that, by definition, breaks the right-left symmetry. So you have a system that is performing some Brownian motion on this ratchet. Is it going to go in one direction? The answer is no, because if I take this x and this x, for example, they have the same potential, so the probability of going from here to here divided by the probability of going to here is 1. So this time reversal symmetry tells me that despite appearances, of course, if the ratchet would be built like this, by symmetry you would know that you cannot go right or left. But why wouldn't you be allowed to go right or left here? The reason is that we have this time reversal symmetry that is forbidding us from doing this. And this is a very subtle symmetry. So what happens if now I do anything to this ratchet? For example, make it flashing. The potential turns on and off. So you do a bit of normal diffusion without nothing, a bit with the potential. Or, I don't know, in 2 dimensions, I make something, some forces that, well, or I do a combination of baths that breaks this symmetry, that is not an equilibrium bath. Well, the system will drift in one direction or the other depending on the details of the bath. Why? The correct answer to the question, why would it drift in one direction to the other, is why not? And this is true about the fish also. Do I know that a fish, given that it is not Brownian, this trap will work? Well, I don't know if this trap will work, but either this trap or this trap, and that depends on, of course, fish behavior, will work. But once I do something like that, I know that there is no reason why the probability of being inside divided by outside is the ratio of volumes. That comes from that time reversal symmetry. So the question is, why does this trap work? The answer is, why not? Simply because I don't have equilibrium, I don't have detail balance, then the answer is why not. I'm going to explore the why nots more the next lecture.